Hello and welcome to our astronomy course. Today we will be continuing study the stars. Okay? So the topic of today's lecture, the family of stars. If you see a light on a dark highway, it is hard to tell how bright it really is. It could be the brilliant headlight on a distance truck or the dim headlight on a nearby bicycle. Let's look at this slide, please. How bright an object looks depends not only on how much light it emits, but also on its distance. A 6 magnitude star, just visible to your eye, look faint, but its apparent magnitude doesn't tell you how luminous it really is. Now that you know how to find the distance to star, I hope you remember this, right? So you can use those distances to figure out the intrinsic brightness of the star. Intrinsic means belonging to the things. So the intrinsic brightness of a star refers to the total amount of light the star emits. When you look at a bright light, your eyes respond to the visual wavelength energy falling on your eye's retina. The apparent brightness you perceive is related to the flux of energy entering your eye. Flux is the energy of joules per second falling on 1 square meter. Recall that a joule is about as much energy as is released when an apple falls from a table onto the floor. 1 joule per second is 1 watt, a common unit of energy consumption used, for example, to rate light bulbs. The apparent brightness of a light source is related in a simple way to its distance. Imagine that you enclosed a light bulb at the center of the special screen. The light that falls on a single square meter of that screen is shown in yellow in this slide. Now, imagine that you doubled the size of the spherical screen. The light that used to cover 1 square meter is now spread out to cover 4 square meters. Now, any spot on the larger screen receives only 1/4 as much flux as a spot on the smaller screen. Likewise, if you triple the size of the spherical screen, a spot on the screen would receive only 1/9 as much flux. The flux is universally proportional to the square of the distance from the source. This is known as the inverse square relation. Now you can understand how the brightness of any light source depends on its distance. Its brightness is reduced in proportional to the square of its distance. And that is an important clue to the intrinsic brightness of a star. If you know the apparent magnitude of a star and its distance from Earth, you can use the inverse square law to correct for distance and learn the intrinsic brightness of the star. Astronomers do that using a special kind of magnitude scale described in the next section. If all stars were the same distance from Earth, you could compare one with another and decide which was emitting light and which less. Right? Okay. Of course, the stars are scattered on different distances, and you can't show them around to line them up for comparison. If, however, you know the distance to a star, you can use the inverse square relation to calculate the brightness the star would have at some standard distance. Astronomers have adopted 10 parsec as a standard distance and refer to the apparent visual magnitude a star would have if it were 10 parsec away as its absolute visual magnitude. This is an expression of the intrinsic brightness of the star. The symbol for above absolute visual magnitude is a capital M with a subscript of V. So, as you can see here, capital M with subscript of V, okay? The subscript reminds you it is a visual magnitude based only on the wavelengths of the light you can see. Other magnitude systems are based on other parts of the electromagnetic spectrum, such as the infrared and ultraviolet. It is not difficult to find the absolute visual magnitude of a nearby star. You begin by measuring the apparent visual magnitude, which is an easy task in astronomy. Then you find the distance to the star. If the star is nearby, you can measure its parallax and from that find the distance. Are you agree with me? Nice. Let's go on. Once you know the distance, you can use a simple formula to correct the apparent visual magnitude for the distance. And so you may find the absolute visual magnitude. Let's see at this slide, please. How does the sun stack up against other stars? Astronomers can find the sun's absolute visual magnitude because they know the distance to the sun and can measure its apparent visual magnitude. The sun is tremendously bright in the sky, but it is very close. Its absolute visual magnitude is only 4.83. If the sun were only 10 parsec from Earth, not a great distance in astronomy, by the way, it would look no brighter than the funniest star in the handle of the Little Dipper. The intrinsically brightness stars known have absolute visual magnitudes of about -8, which means that such a star 10 parsec from Earth would be nearby as bright as the moon. Such stars are 13 magnitudes brighter than the sun, so they must be emitting over 100,000 times lighter than the sun. Yet, the intrinsically finest stars have absolute visual magnitudes of +15 or fainter. They are 10 magnitudes fainter than the sun, meaning they are emitting 10,000 times less light than the sun. The detour to find the distance to stars had led you to absolute visual magnitude, and to some new insights into what stars are like. One last step will tell you how much energy stars generate. The luminosity of a star is the total energy of the star radiates in 1 second. Hot stars emit a great deal of ultraviolet radiation that you can't see, and cool stars emit infrared. Because absolute visual magnitude includes only visible radiation, and so astronomers must add a small correction to make up for the invisible energy. Then they can calculate the luminosity of the star from its absolute magnitude. To make that calculation, you compare the star with the sun. If the corrected absolute magnitude of the star is 1 magnitude brighter than the sun, then it must be 2.5 times more luminous. If it is 5 magnitudes brighter, then it must be 100 times more luminous. Astronomers would write the luminosity of the first star as 2.5 times L with subscribed the symbol of star with dot in the middle. Okay? And the luminosity of the second star as 100 luminosity of the sun. To find the luminosity of a star in joules per second, you can just multiply by the luminosity of the sun, 3.8 times 10^26 joule per second. For example, favorite star Aldebaran has a luminosity of about 150 luminosity of sun, which corresponds to 6 times 10 and 28 joule per second. Okay? The most luminous stars emit roughly 1,000,000 times more energy than the sun. And the least luminous stars emit over 1,000 times less. Also, stars look similar in the sky. They can emit astonishing different amounts of energy. The most luminous emit at least 1,000,000,000 times more energy per second than the least luminous. And clearly, the family of stars contains some interesting characters. How can 2 stars look the same in the sky but have dramatically different luminosities? You can answer this question by building a scientific argument that relates 3 factors: the appearance of a star, its true luminosity, and its distance. The farther away a star is, the fainter it looks, and that is just the inverse square law. Favorite star Vega and Rigel have the same apparent visual magnitude, so your eyes must be receiving the same amount of light from them. Right? Okay, but Rigel is much more luminous than Vega, so it must be farther away. Do you agree with me? Okay, parallax observation from the Hipparcos satellite confirm that Rigel is 31 times farther away than Vega. Distance is often the key to understanding the brightness of stars. But temperature can also be important. Build a scientific argument to answer the following. Why must astronomers make a correction in converting the absolute visual magnitude of very hot or very cool stars into luminosity? How about the stars? Earlier, You learned that blue stars are hot and red stars are cool. So color can give you approximate temperature. But you will need accurate temperatures later in this lecture when you discuss the diameters of stars, and stellar spectra are filled with clues to the temperature of the stars. Stars are very hot deep inside, but the light that forms a spectrum comes from the gases of the surface. So, the spectrum tells you about the surface. Also, astronomers look at all of the spectral lines in a star spectrum. The most important lines in this discussion are the Balmer lines of hydrogen. You can use the hydrogen Balmer lines in a star spectrum like a thermometer. This Balmer thermometer works because the strength of the Balmer lines depend on the temperature of the star's surface layers. Both hot and cool stars have weak Balmer lines, but medium temperature stars have strong Balmer lines. The Balmer absorption lines are produced only by atoms with electrons in the second energy level. If the star is cool, there are few violent collisions between atoms to excite the electrons. So, the electrons of most atoms are in the ground state. Electrons in the ground state can't absorb photons in the Balmer series. As a result, you should expect to find weak Balmer absorption lines in the spectra of cool stars. In the surface layers of the hot stars, on the other hand, there are many violent collisions between atoms. These collisions can excite electrons to high energy levels or ionize some atoms by knocking the electrons out of the atom. Consequently, there are few hydrogen atoms with their electrons in the second orbit to form Balmer absorption lines. Hot stars, like cool stars, have weak Balmer absorption lines. In stars of an intermediate temperature, roughly 10,000 Kelvin, the collisions are just right to excite large numbers of electrons into the second energy level. The gas absorption Balmer wavelengths photons very well and produces strong Balmer lines. Theoretical calculations can predict just how strong the Balmer lines should be for stars of various temperatures. Such calculations are the key to finding temperatures from stellar spectra. The curve in this figure shows the strength of the Balmer lines for various stellar temperature. But you can see from the graph that a star with Balmer lines of a certain strength might have either of two temperatures, one high and one low. How do you know which is right? You must examine other spectral lines to choose the correct temperature. You have seen how the strength of the Balmer lines depends on the temperature. Temperature has a similar effect on the spectral lines of other elements. But the temperature at which the lines reach their maximum strength differs from each element. If you may see on the left side of this slide on the figure B. If you add a number of chemical elements to your graphs, you get a powerful aid for finding the star's temperature. This you may see on the right part of this slide on the figure C. Now you can determine a star's temperature by comparing the strength of its spectral lines with your graphs. For instance, if you recorded the spectrum of a star and found medium strength Balmer lines and strong helium lines, you could conclude that it had a temperature of about 20,000 Kelvin. But if the star had weak hydrogen lines and strong lines of ionized iron, you would assign it a temperature of about 5800 Kelvin, similar to that of our sun. The spectra of stars cooler than about 3000 Kelvin contain dark bands produced by molecules such as titanium oxide, TO. Because of their structure, molecules can absorb photons at many wavelengths, producing numerous, closely spaced spectral lines and blend together to form bands. These molecular bands appear only in the spectra of the coolest stars, because molecules in cool stars are not subject to the violent collisions that would break them apart in hotter stars. From stellar spectra, astronomers have found that the hottest stars have surface temperatures about 40,000 Kelvin and the coolest about 2000 Kelvin. Compare this with the surface temperature of the Sun, about 5800 Kelvin. You have seen that the strength of spectral lines depend on the surface temperature of the Sun. From this, you can conclude that all stars of a given temperature should have similar spectra, right? Is it logical? If you learn to recognize the pattern of spectral lines produced by 6000 Kelvin star, for instance, you need not use figure C every time you see that kind of spectrum. You can save time by classifying stellar spectra rather than analyzing each one individually. The first widely used classification system was devised by astronomers at Harvard during the 1890s and 1900. One of the astronomers, Annie J. Cannon, personally inspected and classified the spectra of over 250,000 stars. The spectra were first classified into groups labeled A through Q, but some groups were later dropped, merged with others, or reordered. The final classification includes the 7 major spectral classes or types still used today, like O, B, A, F, G, K, and M. Okay? As like you may see this on this slide. This sequence of spectral types, called the spectral sequence, is important because it is a temperature sequence. The O stars are the hottest, and the temperature decreases along the sequence to the M stars, the coolest. For maximum precision, astronomers divide each spectral class into 10 subclasses. For example, spectral class A consists of the subclasses A0, A1, A2, and so on, up to A9. Next come F0, F1, F2, and so on. This fine division gives a star's temperature to an accuracy within about 5%. The Sun, for example, is not just a G star, but a G2 star. And this table breaks down some of the information in Figure C and presents it in tabular form according to the spectral class. For example, if a star has weak Balmer lines and lines of ionized helium, it must be an O star, right? 13 stellar spectra are arranged in this figure, from the hottest at the top to the coolest at the bottom. You can easily see how the strength of the spectral lines depends on temperature. The Balmer lines are strongest in A stars, where the temperature is moderate but still high enough to excite the electrons in hydrogen atoms to the second energy level, where they can absorb Balmer waveless photons. In the hottest stars O and B, the Balmer lines are weak because the higher temperature excites the electrons to energy level above the second or ionized the atoms. The Balmer lines in cooler stars like F through M are also weak, but for a different reason. The lower temperature cannot excite many electrons to the second energy level, so few hydrogen atoms are capable of absorbing Balmer wavelength photons. Also, these spectra are attractive, and astronomers rarely work with spectra as color images. Rather, they display spectra as graphs of intensity versus wavelengths that show dark absorption lines as dips in the graphs. Let's look at this figure, please. Such graphs allow more detailed analysis than photographs. And notice, for example, that the overall curves are similar to black body curves. The wavelength of maximum intensity is in the infrared for the coolest stars and in the ultraviolet for the hottest stars. Look carefully at these graphs, and you can see that helium is visible only in the spectra of the hottest classes and titanium oxide bands only in the coolest. Two lines of ionized calcium increase in strength from A to K and then decrease from K through M. Because the strength of these spectral lines depend on temperature, and it requires only a few moments to study a star spectrum and determine its temperature. Now you can learn something new about your favorite stars. Sirius, brilliant in the winter sky, is an A1 star, and Vega, bright overhead in the summer sky, is A0 star. They have nearly the same temperature and color, and both have strong Balmer lines in their spectra. The bright red star in Orion is Betelgeuse, a cool M2 star, but blue-white Rigel is a hot B8 star. Polaris, the North Star, is an F8 star, a bit hotter than our Sun. And Alpha Centauri, the closest star to the Sun, seems to be a G2 star, just like our Sun. The study of spectral types is a century old, but astronomers continue to discover new types of stars. The RL dwarfs found in 1998 are cooler and fainter than M stars. The spectra of L dwarf show that they are clearly a different type of star. The spectra of M stars contain bands produced by metal oxide, such as titanium oxide. But L dwarf spectra contain bands produced by molecules such as iron hydride, ferrum H. The T dwarf, discovered in 2000 years, are even cooler and fainter than L dwarfs. Their spectra show absorption by methane, CH4, and water vapor. Look at this figure, please. The development of giant telescopes and highly sensitive infrared cameras and spectrographs is allowing astronomers to find and study these coolest of stars. Identifying the elements that are present in a star by identifying the lines in the star spectrum is a relatively straightforward procedure. For example, two dark absorption lines appear in the yellow region of the solar spectrum at the wavelengths of 589 nanometer and 589.6 nanometer. The only atom that can produce this pair of lines is sodium. So the sun must contain sodium, right? Okay. Over 90 elements in the sun have been identified this way. However, just because the spectral lines characteristic of an element is missing, you cannot conclude that the element itself is absent. For example, the hydrogen-Balmer lines are weak in the sun's spectrum, even though 90% of the atoms in the sun are hydrogen. This is because the sun is too cool to produce strong Balmer lines. Astronomers must consider that an element's spectral lines may be absent from a star spectrum because the star is too cool or too hot to excite those atoms to the energy levels that produce visible spectral lines. To derive accurate chemical abundances, astronomers must use the physics that describe the interaction of light and matter. To analyze a star spectrum, take into account the star's temperature and calculate the amounts of the elements present in the star. Such results show that nearly all stars have composition similar to the sun's. About 91% of the atoms are hydrogen, and 8.9% are helium, with small traces of heavier elements, as you can see in this table. You will use these results in later lectures when you study the life stories of the stars, the history of our galaxy, and the origin of the universe. Now that you know the luminosities of stars, you can find their diameters. You know little about stars until you know their diameters. Are they all the same size as the sun? Or are some larger and some smaller? How do you think? Recall that astronomers cannot see the stars as disks through astronomical telescopes. Nevertheless, there is a way to find out how big stars really are. If you know their temperatures and luminosities, you can find their diameter. This relationship will introduce you to the most important diagram in astronomy, where you will discover more of the star's family secrets. To use the luminosity and temperature of a star, to learn its diameter, you must first understand the two factors that affect a star's luminosity: surface area and temperature. Okay? You can eat dinner by candlelight because a candle flame has a small surface area. Also, the flame is very hot. It cannot radiate much heat. It has a low luminosity. However, if the candle flame were more than 3 meters tall, it would have a very large surface area from which to radiate, and also it might be no hotter than a normal candle flame. Its luminosity would drive you from the table. Let's look at this figure, please. In a similar way, a hot star may not be very luminous if it has a small surface area. It could be highly luminous, however, if it were larger and had a larger surface area from which to radiate. Even a cool star could be a luminous if it had a large surface area. Because of this dependence on both temperature and surface area, you need to separate the effects of temperature and surface area, and then you can find the diameter of stars. Let's see this slide, please. Astronomers use a special diagram to sort the stars by temperature and size. The Hertzsprung-Russell, or so often called HR diagram, named after its originators, Ejnar Hertzsprung and Henry Horace Russell, is a graph that separates the effect of temperature and surface area on stellar luminosities and enables astronomers to sort stars according to their diameters. Before you explore the details of HR diagram, try looking at a similar diagram you might use to sort automobiles. You can plot a diagram such as this figure, showing horsepower versus weight for various makes of cars. In general, the more car weighs, the more horsepower it has. Most cars fall somewhere along the sequence of cars, running from heavy, high-powered cars to the upper left to light, low-powered models at the lower right. You might call this the main sequence of car. But some cars have much more horsepower than normal for their weight, the sport or racing models, and lie higher in the diagram. Okay? Other cars, the economy models, have less power than normal for cars of the same weight and fall lower in the diagram. Just as this diagram sorts of cars into family groups, and so the HR diagram sorts of stars into the groups according to the height. The HR diagram is a graph with luminosity on the vertical axis and temperature on the horizontal axis. A star is represented by a point on the graph that marks its luminosity and its temperature. The HR diagram in this figure also contains a scale of spectral type across the top, because the star spectral type is determined by its temperature, and you could use either spectral type or temperature on the horizontal axis. In an HR diagram, the location of a point tells you a great deal about the star it represents. Points near the top of the diagram represents very luminous stars, and points near the bottom represents very low luminosity stars. Also, points near the right edge of the diagram represent very cool stars, and points near the left edge of the diagram represent very hot stars. Notice in the HI diagram in this figure how the artist has used color to represent temperature. In a photograph, the red stars are cool and blue stars are hot. Astronomy use HR diagrams so often that they usually skip the words, the point that represent the star. Rather, they will say that a star is located in a certain place in the diagram. The location of a star in HR diagram has nothing to do with the location of the star in space. Be careful, okay? Furthermore, a star may move in the HR diagram as it ages and its luminosity and temperature change. But such motion in the diagram has nothing to do with the star's motion in the space. The main sequence in the region of the HR diagram, running from upper left to lower right. It includes roughly 90% of all normal stars. In this figure, the main sequence is represented by a carved line with dots for stars plotted along it. As you might expect, the hot main sequence stars are more luminous than the cool main sequence stars. And notice in the HR diagram that say some cool stars lit above the main sequence. Also, they are cool, they are luminous, very little surface area from which to radiate, and that limits them to the luminosity. I think it's enough for today. Okay? Any questions or proposition? I hope you enjoyed this lecture and I'm looking forward to see you next time. Bye.